Let's secure our TCP/IP traffic. There are lots of ways we can secure our traffic. One of the ways we can do that is using encryption, and we're going to talk about how to encrypt files and symmetric and asymmetric encryption and the difference, and also what the difference is in the security level. And we'll talk about hashing and AAA authentication. Another big part is access control, and we'll use Kerberos and Eap to secure our transmission as well as certificates. And we'll talk about spanning tree protocol, denial of service, and how to spoof. So what is encryption? Encryption is the process of obfuscating data so it can only be read by someone who is authorized. And we can refer to that person as the key holder. Encryption keeps people from spying on our information and stealing it. Encryption can protect you while you browse the web, while you do shopping online, while you use your banking online, and use messaging apps as well. End-to-end encryption is a form of encryption in which only the sender and intended recipient are going to be able to read that message. No one, including the party providing the communication service or any third-party application, has knowledge of what the encryption key is. End-to-end encryption is the most secure form of encryption, so where possible, always use end-to-end encryption to protect your data. Let's take a look at a demo of how we can encrypt our files on a Windows computer. Let's take a look at how we can encrypt a file or folder. I'm going to right-click and choose New Folder, and I'm going to type it in, Encrypted. And I'm going to open it up. I'm going to create a new text document, and we'll just call it Test. Now let's go back to our C drive and take our encrypted folder, and we'll right-click on it, and we'll go to Property. So what we're going to do is we're going to turn on what's called the Encrypting File Service, which is installed by default. But once we use it, it creates a certificate that is going to encrypt the files for us. So we go to Advanced, and we check the box that says Encrypt Contents to Secure Data. Click OK, and then we click Apply. And we want to apply it to not only the folder, but all the files inside it. Now, if you have a lot of files in here, it could take quite a while to encrypt all of them, so just be ready for that. And it's also mentioning we should back up our key. So if we go to Advanced and we click on Details, we can see that we now have a certificate that's assigned to this particular encryption. And if we open up something called the MMC, or Microsoft Management Console, then we can see our certificate by adding the snap in. So we'll go to Certificates, and we'll say it's our user account because it was encrypted using our user account. And there's our certificate. So we can take the advice of the pop-up that said back up your keys, and we can do that by backing up the certificate. So we right-click on our certificate, go to All Tasks, and go to Export. And we get a wizard that comes up, and we say, yes, also export the private key. We're going to need that if we're going to back it up. Click Next, and give it a password, and confirm it. Click Next. Now we need a file name. So I'll just put this on the desktop and just call it EFS for Encrypting File System. Save. And finish. Now I can take that certificate and I can copy it to another location. So that way, if I ever lose or my certificate gets corrupted, then I'll still be able to decrypt my files that have been encrypted using the certificate, because without it, I will never be able to get that data back. So that's how we encrypt our data using EFS. Symmetric key encryption, and that's a type of encryption where only one key, also called a secret key, is used for both encryption and decryption. The sender and receiver sends the data via symmetric encryption, and that must exchange the key so that it can be used in a decryption process. This is much different from asymmetric encryption, where a pair of keys, you have a public one and a private one, is used to encrypt and decrypt the messages. When you use symmetric encryption, your data is converted to a form that cannot be understood by anyone who does not possess that key that they need to decrypt it. Once the intended person or the key holder tries to open the message, the algorithm reverses its action and the message can now be read and understood. Once the file is closed, it reverts back to its encrypted state. Now let's cover asymmetric encryption. Asymmetric encryption is a lot more complicated than symmetric encryption. It's also known as public key cryptography. And this is a newer method compared to the symmetric type of encryption. Asymmetric encryption is going to use 2 keys instead of just 1. These keys can be exchanged either internally or across the internet. If you're using symmetric encryption, anyone with a secret key can decrypt that message. That's why asymmetrical encryption uses 2 keys, which makes it a lot more secure. A message encrypted using a public key can only be decrypted using a private key. A message encrypted using a private key can only be decrypted using a public key as well. And strangely enough, the public key is not required to be safe because it is publicly available and can be passed over the internet. To make asymmetric key encryption work, you've got to have a way of discovering the public keys and the private keys. One technique is using digital certificates in a client-server model. The certificate or package identifies a user and a server. It contains information such as the name of the organization or the organization that issued the certificate. It may also include an email address, as well as a country or state, as well as the user's public key. Now here's where it gets interesting. When the server and the client require the secure encrypted communication, they send that information over the network to the other party, and then that other party sends back a copy of the certificate. The other party's public key can then be extracted from the certificate that was sent over the internet. A certificate can also be used uniquely to identify the person who owns it. SSL as well as TLS both use asymmetric and symmetric encryption. SSL stands for Secure Socket Layer, and TLS stands for Transport Layer Security. Although we commonly call shopping online using a certificate SSL for Secure Socket Layer, what we're actually using nowadays is TLS, which has replaced the older SSL technology. We need a way to secure the transmission of our message, and that's where hashing comes in. So what is hashing? Well, it's a one-way process of message transmission. When the message is intended for a particular person, there's a formula that's going to generate the hash, and that helps to protect the security of the transmission against any kind of tampering. Hashing is also a method of sorting various different key values in a database table, and it does it very efficiently. When users send a secure message, a hash of the intended message is created, and then it's encrypted, and it's sent along with the message. When the message is received, the receiver is then going to decrypt that hash as well as the message. Then something interesting happens. The receiver creates another hash from the message. Now, these 2 hashes have to be identical when they're compared. Otherwise, a transmission error might have occurred. The hashing process basically makes sure that we know on both ends that the message was not altered by anyone unauthorized. AAA also helps us secure our messages when they're sent from one person to another. Let's find out how. So what is AAA? AAA stands for Authentication, Authorization, and Accounting. So saying AAA Authentication is a little bit of a misnomer because authentication is already in the first letter A, but it's an easier way to refer to it. And what it does is it controls access to computer data. It enforces policy as well as auditing. When you combine all these processes together, it's considered important for effective network security. The first process is called authentication, and it provides a way of identifying the user. So when you enter a username and password to log into your computer, you're actually authenticating using that username and password. A AAA server compares the user's authentication credentials with other user credentials stored in that AAA database. Now, if they match, the user is granted access. After you have authentication, a user must gain authorization for doing various different tasks, such as accessing resources like data. After logging into a computer, the user may try to issue some commands. The authorization process determines whether that user has the authority to do such. Authorization is the process of basically enforcing the policies that were created by the person who set up the computer. It determines what types or qualities of activities or services that a user can do. How do we keep people off a computer that they shouldn't be using? Well, we do it using access control. We need to keep people off a network or off of a computer until they've provided their authentication. When we keep them off a network, it's called network access control. And the most common type of network access control is a standard that was developed called 802.1x. And we install this onto switch ports or onto a smart switch that runs at both layer 3 as well as layer 2. Network access control uses port-based access control. And this has to do with the physical interfaces of the switch or physical access to our network. 802.1x is authentication, but it's assigned to ports on a switch rather than a username and password on a computer. There's 3 different kinds of devices that communicate using the 802.1x process that we use for authentication. The first one is called the supplicant, and that's usually going to be software, a software client actually, that's running on a device such as a VPN client. Many of us use VPNs to get into our office while we're remoted in from a hotel, home, or other location. And that's using the supplicant type. When we talk about the authenticator, we're talking about a AAA server that's on the back end, such as a server or firewall at the office. This is going to check the username and password against the database. The database is the third part of our access control. That can either reside on the same server as the authenticator or as a separate server that connects to it by the authenticator. We have other ways to control access to our network, and that's MAC address filtering. And remember, the MAC address is the hardware address. This is the address that's burned into our network interface card when the card is created. We can turn on what's called a MAC filter to control access to our network. So we can say, if you have this MAC address on your card, then you're allowed onto our network. Or you can say the opposite. You can say if you have this particular MAC address, you're not going to be allowed on our network. This is referred to as a captive portal. So in other words, you're going to be going into this portal, and the portal's going to take a look at this information and decide whether or not you're going to be allowed any further. If you are, then you get to go on from the portal into the network. If not, you're stopped and spun around, just like a man trap, say, in a data center. Another type of access control is using what's called access control lists. And instead of checking the MAC address, it checks the list of allowed IP addresses. And we can do that both inbound and outbound, such as on a firewall. And it checks the type of port traffic, what types of TCP or UDP ports or other types of port traffic are going to be allowed in or out. So we have both our IP being filtered as well as the ports themselves. Access control lists can be set up on a firewall, on a switch, on a router, a computer, or server. Kerberos and Eap are used on modern servers, and they're used a lot on Windows servers as well. So what is Kerberos? Well, it uses symmetric key cryptography and requires a trusted third-party authorization that's going to verify whether or not the person is who they say they are. Kerberos Authentication is the default authorization technology used by Microsoft Windows, but you can also find it in Apple operating systems, FreeBSD, Unix, and other forms of Linux. It does provide better security than prior to Windows Server 2000. In Windows NT, Microsoft used the NT LAN Manager, but it had a lot of security holes in it. Kerberos was a much better improvement on those previous authorization technologies because it used a much stronger cryptography and a third-party ticket authorization. And those two together made it much more difficult for cyber criminals to get onto your network. The big difference between NTLM or NT LAN Manager and Kerberos is that third-party verification as well as the stronger encryption. So here are the Kerberos steps it takes when a client is going to request something from a server or computer. The client is going to request an authentication ticket from the key distribution center. After the KDC verifies the credentials of the user, it's going to send back an encrypted TGT and the session key. The TGT is another way of saying authentication ticket. The TGT is encrypted using the ticket granting service, or the TGS. And the TGS provides a secret key. The client is going to store that TGT, and when it's going to expire, the local session manager is going to request another one, and then the process starts all over again. And this entire process is going to be transparent to the user. There are some hacks for Kerberos, however. The first one is going to be the pass the ticket hack, which forges the session key. And it's basically the process of forging the session key, and then it presents the forgery to the resource as valid credentials. The next one is gold and silver tickets. A golden ticket is a ticket that grants a user domain admin access. However, a silver ticket is a forged ticket that grants access to a service. However, admin access has access to all services, whereas a silver ticket is going to access to a specific service. So depending on which service it accesses, it could end up with the same amount of access in the long run. The next one would be a skeleton key. And this is malware that can bypass Kerberos, but the attack must first have that golden ticket to have admin access. Now we have the DC shadow attack, which is a newer attack, and that's where attackers can gain enough access inside a network where they set up their own domain controller to use in further hacking and infiltration. Extensible authentication protocol is used for wireless and point-to-point. And an example of this would be a VPN, where you have a point-to-point VPN tunnel that allows you to connect two networks in two different places. And it's used in wireless as well to authenticate users as they access the network. It uses a type of multi-factor authentication, and that can include tokens, smart cards, certificates, one-time passwords, and public key infrastructure, public and private certificates. So here's how EAP works. A user is going to make a request through an access point. The user requests connection to a wireless network, for instance, through the access point, which is the location where users can find the SSID that's being broadcast and then be prompted for the username and password. The access point requests the ID and transmits that information over to the authentication server. Authentication servers then ask for proof of ID, and once that ID is provided, the user is connected. Certificates can mean a lot of different things. There are certificates that have wildcards in them, there's certificates that have multiple names in them, and there's simple certificates, as well as ones provided in Active Directory. So let's talk about those. Certificates provide identification as well as help us with authentication. So the person with whom we're trying to communicate wants to know they are who they say they are. Otherwise, we're going to have to assume that it's a hacker or attacker who's trying to steal our information. Confidentiality is also a big part of certificates. Information secured by certificates may only be read and understood by the sender and receiver. There's also integrity involved. Using certificates, we understand that the information was not tampered with during the transportation. We also use certificates for non-repudiation. The sender cannot deny sending the message, and the receiver cannot deny receiving it. Certificates also provide us with access control. Access is going to be protected information that's only going to be realized by the person who's supposed to receive it. We use certificates for trusted documents. Many contracts have been secured using certificates. The certification authority has the root certificate, and the root certificate must be protected at all costs, because from this root certificate we create all other certificates underneath it. Certificates are governed by the vendors that issue them, and the vendors can be public entities or it could be Active Directory. We use SSL or TLS. Now, SSL was used previously, but now we're using TLS. So SSL stands for Secure Socket Layer, and TLS stands for Transport Layer Security. All certificates nowadays are made using this Transport Layer Security, which is even better security than SSL was prior. The certificate issued, we know, was provided by the domain owner, by a trusted certification authority. And the data that's going to be transacted is going to be encrypted to provide transactional security as well. There's many different types of trusted certificates that you can purchase or issue from Active Directory. You can also get something called a multi-domain or SAN certificate, which stands for Subject Alternative Names. And that's used a lot of the times by companies that may have an Exchange server. And it allows you to use multiple names all in one certificate. And you can even have multiple domains as well. These certificates cost a little bit more. For instance, you could have mail.domain.com or mail.domain2.com. They typically come with up to 4 names, but you can purchase additional names to be added to the certificate if you need them. The wildcard costs the most of any of these certificates, but you can have many subdomain names, and you can save money if you're going to end up needing to buy a lot of certificates anyway. A good example would be here. We see adomain.com, B, and C domain, and you can keep going with as many as you want. They all have to end in domain.com if that's the name of your domain, but you can have as many subnames as you like. You can issue a certificate from Windows domain controllers by using the trusted group policy settings. For instance, your first certificate is going to be the root certificate, and it's going to be issued to whatever the name of your domain is. And an example would be root.domain.local. And from there, you can create additional certificates such as the application.domain.local or SQL.domain.local or www, whatever it is you'd like. Now, those are only going to be trusted by any computers that are inside the domain controller or the Active Directory domain itself. They're not going to be trusted by public users. That's why you need to use a public entity for publicly facing computers and servers. Spanning tree protocol is a very useful protocol that we use on bridges and switches and other devices. It has the designation of 802.1d with the IEEE, and it was originally designed for bridges and switches for use on local area networks. Its main purpose was to prevent bridge loops. And that's what happens when you have redundant paths in your network. The easiest way to give an example of this is if you have a connection into a switch that loopbacks into itself. For instance, if we have a cable plugged into port 1 and the other end of that cable is plugged into port 2 of a switch, that creates a loop. And it happens in networks that have a lot of cables going all different directions and a lot of different network administrators that end up making a mistake. So what it does is it disables the inactive and looped ports, so that way you don't end up with a broadcast storm. And it also creates fault tolerance, because a single fault will not end up bringing down the entire switch. Now, if you set up a port with trunking, that means you're going to allow multiple different VLANs connected, and you're going to be connecting one switch to another switch. So those are called trunk ports. So it's turned off on those ports. However, on regular switch ports that are plugged into endpoints such as computers, you can have STP turned on. There's lots of different denial of service attacks out there. Let's take a look at those. A denial of service attack happens when legitimate users cannot get any work done. And it happens because of a cyber attack. When a lot of infected computers all try to attack the same destination all at the same time. And they typically use the ping attack to do that, just as you see here. It floods the network with data and it fills up the internet pipe. There's several different types of denial of service attacks. The first one would be a Smurf attack. And that's when the attacker sends the ICMP, or the ping as you see here, broadcast packets to a lot of different computers with a spoofed source internet protocol. The recipients of these spoofed packets will then respond, and the targeted host is going to be flooded with a lot of different responses. The next one would be a Syn Flood, and that occurs when an attacker sends a request to connect to the target server, but it never actually completes the connection. So you've got to have something that's called a three-way handshake in order to connect using any type of TCP transaction. However, if you only send the first of those 3 handshakes through and then pull your hand away and then do that thousands of times a second per computer, then that's really going to mess up the receiving computer from being able to do any business. So it leaves that connected port on an occupied status, and it makes it unavailable for any further requests. Once all the open ports are filled up, Legitimate users cannot connect to that server any longer. DDoS stands for a distributed denial of service attack. That occurs when many different machines are operating together to attack one target. Sometimes you get many different DDoS attackers together and they create what's called a botnet. And that is a group of hijacked connected computers out to the internet who take on large-scale attacks. You can bring down an entire government, banking system, financial system, utilities, all making it impossible to provide any type of service. An example of that would be when Russia attacked the country of Georgia, and they kept them from having any type of financial services because they did a distributed denial of service attack using a botnet, and it made it impossible to move any money around in the country. Let's take a look at a rudimentary denial of service attack just to give you an idea of how it works. Let's take a look at how we can create a denial of service attack using the ping utility. So we can type in ping, and I'm following that up with an internal IP address. Now, it's not legal to take down someone else's service, so I'm just going to work on my own just as an example. So if I do a simple ping, this really isn't a denial of service. I'm just sending out 32 bytes, and it's giving me a 1 millisecond response. Fantastic. What I can do to make this a little bit harder on my connection is to do a -L and to make it 4,000 bytes. There we go. Now I can do a -T, which will continuously ping it. And now it's continuously pinging it. So what I'm going to do next is I'm going to pretend like I'm opening another computer, and I'm going to do the same thing. And now I'm going to open up several more boxes. And I'm going to increase the size of the packet to 40,000 from 4,000. So you can see we're already getting to 2 milliseconds. And now I've gone to the max, 65,500 bytes. And now we're up to 3 milliseconds. So you can see that if you had thousands of computers all sending the maximum amount of data all at the same time, eventually that would get to a much larger number, and then eventually the entire pipe would get filled up and you wouldn't be able to send any more data at all. This is how a distributed denial of service attack works. And it can bring down governments, it can bring down organizations, it can bring down banks, and it can basically bring down anybody that's out on the internet. And although there's not a lot of money in creating a distributed denial of service attack, there is a way that you can bring down a competitor, you can bring down a foreign government. So you can gain a competitive advantage by having a DDoS work for you, and that's why people do it. IP spoofing is a way that hackers can get into a network by pretending to be someone else. So what IP spoofing does is it avoids discovery by pretending to be someone they're not. So they spoof their source IP address, and that's going to impersonate another computer or system, and it's going to hide the identity of the sender or both. The header field for the source IP is going to contain an address that is different from the actual source IP, and it bypasses security. So if you're using access control lists, it bypasses security by pretending to be on an IP address that is in an allowed access control list. And that's why we use firewalls nowadays, because when the internet was new and companies were getting on the internet, they used access control lists only, and hackers soon realized they could bypass the security by spoofing the addresses. Firewalls, on the other hand, are not going to be spoofed. So here's how it works in IP spoofing. An attacker is going to modify the source address and the outgoing packet. And that destination computer treats the packet as if it's coming from a trusted source. So the computer is going to accept that as being from a trusted source because there's really no external signs that any kind of tampering is going on. One way to protect against this is to monitor your network for any kind of spikes in activity that would be atypical for your network. You can also set up packet filtering systems capable of detecting these types of networks, such as outgoing packets with source IP addresses that don't match those on your own internal network. And you can use robust verification methods for all remote access. So you can use two-factor authentication, firewalls that are aware of IP spoofing, and other products that were created to detect this type of traffic. We covered a lot of information on protecting your computer. such as encryption, and we moved into access control and certificates. We also talked about spanning tree protocol, as well as denial of service and spoofing IP addresses. When it comes to protecting your computer in a lot of different ways, these are the types of topics that you're going to see on your Network Plus test, so review them thoroughly prior to taking the certification test.